Okay, good afternoon, everyone. I am going to show you in a moment some really colorful slides. So that proves that engineers are not a bunch of boring people, okay? But before we do that, we still have to deal with some fundamental issues. Okay? We're going to look at some key provisions in ACI 360 and how it relates to what I'm talking about today. And the importance of establishing the modulus of subgrade reaction, Ks. Looking at historically what has been done in terms of modeling and analysis of slab-on-grade using 2D versus 3D. And then I will provide you some illustrative examples. And that's the colorful part, yeah, the 200 millimeter thick slab, and then a case study. Okay. So in ACI 360, there are these diagrams. So you're wondering, what are they for? So it's talking about the slab-on-grade will actually either curve up or curve down, depending on the thermal gradient. In the summer, when you have the top surface much harder than the bottom, it's going to curve up. In the winter, potentially, the top surface is cooler than the bottom, so it's going to lift up at the corner and the edges. Okay? And then ACI 360 also tells you that, oh, this phenomenon is not going to increase forever. In other words, there's a limit when your size of the slab gets bigger. Up to a point, those mode of deformation changes from a single to double or multiple. And so there's a limit in terms of what would be the maximum thermal effect on the slab. Now, we have to recognize that the slab-on-grade interacts with the ground, okay, depending on the stiffness of the subgrade. The interaction between the slab and the ground generates shear and bending moment diagrams, and depending on the stiffness of the ground, those values changes. And it is also a nonlinear problem in the sense that, obviously, the ground cannot take tension. The slab-on-grade is just sitting on it. So if we are going to do an analysis of this, we have to use nonlinear or compression-only springs. Okay?
Can you read your last bullet? I can read your last bullet point. More suitable for...
Okay. The last bullet point says it's more suitable for working stress design. Okay? Because we cannot combine the individual load cases because it is a nonlinear problem, okay? So if you're doing a limit state design and you have load factors like 1.4, 1.7, whatever, those are fictitious values that at certain ultimate limit state, from a strength point of view, it may reach that, but you cannot do those combinations separately and try to add them, the results together after each individual analysis, because it cannot be superimposed. Okay? And obviously, the soil springs, in the past, people try to come up with mathematical models to solve this problem, and inevitably, that would lead to oversimplifications with a 2D beam on elastic foundation type of analysis, and inevitably, they cannot cancel out so easily if the springs end up in tension. Okay? But today, most of the commercial finite element programs can deal with this problem. Okay? It's just an iterative process, and you have to define the compression-only springs. Okay? Now, in the past, ACI 360 says that there's good agreement between those experimental stresses versus those that were computed by people like Westergaard using those classical beam on elastic foundation theory, okay? So there's a good agreement as long as it remains continuously supported by the subgrade. In other words, it doesn't go into tension, right? But when it does go into tension, then that's where it becomes ambiguous. Ambiguity exists, and it is difficult to determine the correction coefficients for those cases. Okay. Modulus of subgrade reaction. The classical book from Tasagi give us some suggested values. You see, for example, in the middle row, dry or moist sand. The proposed value for medium density is 130 tons per cubic foot. Okay? And then you have this table that came from the American Concrete Pavement Association and the Asphalt Pavement Association. It's based on soil classification. If you look at sand or silty gravel, for example, it's giving you sort of like the same kind of range. It's 150 to 200 PCI. Then in CI 360 itself, it also has this bar chart that relates the KS to CBR, the California bearing ratio. So we do have values that we can use pulling from different sources, okay, for the modulus of subgrade reaction. As I said, from Tasagi, you would have 130 tons per cubic foot. That converts to about 168 PCI. From the American Concrete Pavement Association, it's about 150 to 200 PCI. When you convert that into metric, I'm more used to using metric system. 150 PCI is equal to 40,000 kilonewton per cubic meter. Okay, that translates to about 1,000 kPa for a settlement of 25 millimeters. To me, that is too high. Okay, when we deal with most of the slab-on-grade situation, we might not even know exactly what is underneath, or it is on fill, it's on not very good soil. 40,000 kilonewton per cubic meter is way too high. And remember, those numbers suggested by Tasagi and from the American Concrete Pavement Association, those were based on plate load test, okay? 1 foot by 1 foot plates. And if you know the general theory of the Boussinesq's stress diagram, the bigger your loaded area for the same pressure you are studying, the bigger is the zone of influence, and therefore the bigger is the total settlement, right? So when we are dealing with a large piece of slab, okay, easily 12 meters by 12 meters or 15 meters by 15 meters between expansion joints, and you put a lot of load in that area, we feel that the 150 PCI or 40,000 kilonewton per cubic meter is too high. So we normally use, in our design, we use 20,000 kilonewton per meter cube or 75 PCI for a 5-meter slab, or half of that for an even bigger slab. So we did a lot of parametric studies that probably represent the worst case scenario. So here you see a piece of slab that is expansion joints 12 meters apart, okay? And then we use a KS of 10,000. And when we subject a 200 millimeter slab with a plus 35 degrees C of thermal gradient, meaning it's hotter at the top, okay? So the top wants to expand, right, relative to the bottom. So it curved up, okay? And so when in that state, under its own self-weight, it's already generating positive moment, okay? That means tension at the bottom. So now you see the colorful diagrams, okay? So when we subject the 200 millimeter slab with the plus 35 degree thermal gradient and 12 kPa of uniform life load. 12 kPa is 250 pounds per square foot. That's equivalent to highway loading as a uniform surcharge. Okay? It's cracking the slab. Okay? The tensile stress at the bottom is 4.89 megapascal, whereas according to ACI 318, the modulus of rupture is only 3.27. So it's definitely it will crack the slab. Okay? And that's the equivalent moment intensity. Again, it shows that the actual positive moment in the middle exceeds the cracking moment. Okay? But when we apply the same loading, the same thermal gradient plus 35 degrees C to a 150 millimeter slab, okay, the moment is much reduced. The ratio between the positive moment of a 6-inch slab to an 8-inch slab is about 55%. Okay? Recognizing that the I gross of the 6-inch slab to the 8-inch slab is only 42%. Okay? So this is telling us that it's not necessarily the thicker the slab is better for this problem. The thicker the slab, or the more rigid the slab is, okay, the thermal effect becomes dominant because it needs to overcome that initial curvature. And when you then apply load on it, it will try to flatten it out, and it will cause positive bending moment. Okay? Keep that in mind, the 55% is an interesting number. Okay? What about if we put the 12 kPa or 250 pounds per square foot, only loading one corner of this piece of slab? Okay? It generates even higher tensile stress, okay, 5 point something at the bottom. And that's the corresponding positive bending moment. Okay? But again, if we apply the same load, same thermal gradient to a 6-inch slab, the corresponding positive bending moment is only 55% of that. So this is telling us that not the stiffer, the better. Okay? In fact, if the slab is more flexible, it can conform to the ground better. If the ground needs to deform, you would have a better design if the slab is capable of elastically deforming and conforming to the deformation of the ground. Okay? Now, if I put a point load in the middle, 100 kilonewton, that represents the wheel load of a fully loaded truck plus the impact factor or dynamic load allowance, 10 tons, right in the middle. Okay? So it generates a tensile stress, of course, at the bottom that exceeds the cracking moment. Okay? And the moment is this much. But now, if we compare the 6-inch slab to the 8-inch slab, okay, the ratio becomes 86%. Okay? So it's larger than the 55%, but it's still smaller than the 8-inch slab. Okay? In Canada, we also have to design for the negative thermal gradient because the top can become colder. Okay? So if you subject the slab to minus 25 degrees C, okay, the corners will lift up. So you apply a uniform life load, it will crack the slab at the top. Okay? And again, if you apply the same load, the same thermal gradient to the 6-inch slab, you get 55% of the moment intensity compared to the 8-inch slab. Okay? Is that a coincidence? I don't know. It just came out like this. Okay? So if you apply the 12 kPa at 1/4 of the slab only, you crack the slab as well at the corner. And compared with the 6-inch slab, again, you see this ratio, 55%. Okay? And then we put a point load at the corner. Okay? It will crack the corner. Okay? If you compare it with the 6-inch slab, in this case, the tensile stress at the top for the 6-inch slab is way higher than the 8-inch slab, okay? Because the corner is behaving like a cantilever corner. There's actually a gap underneath. When you apply the point load to it, it will generate a bigger tensile stress at the corner, okay? So what does that mean to us? The study that we have made actually considers many runs of different conditions, but for the time constraint, I can only show you this much. Okay? But what this is telling us is that we can solve this kind of problem quite easily nowadays with finite element program, with plate elements, and compression-only springs. Okay? We should use the appropriate modulus of subgrade reaction based on site condition, but a KS of 10,000, if you have a big piece of slab, 10,000 kilonewton per cubic meter would likely cover the worst case. Okay? You have to include the thermal gradient effect based on your location. Canada versus Mexico is different. Okay? And then we applied a reduction factor of 0.4 to the gross section stiffness. Okay? I showed you just now the eye growth of the 6-inch slab is conveniently about 40% of that of the 8-inch slab. So what we're saying here is if you have an 8-inch slab, and when you do the finite element analysis, consider the actual refractive stiffness of the 8-inch slab to be 40% of the actual. Because if the slab cracks, and if you do the saw cuts at every, 12 feet or something like that, okay, it will make the slab more flexible. Okay? So by reducing the stiffness of the slab to 40% of the gross area, you would get a more realistic response from the ground. Okay? And then design the GFRP using transformed crack section and limiting the working stress to somewhere between 0.3 to 0.4. 0.3 for sustained load, 0.4 perhaps for fatigue effects. Okay? But we have to ensure the factored ultimate moment resistance is bigger than the cracking moment, because we don't want, after multiple times, the actual material stress of the GFRP is exceeded. Introducing more expansion joints or closer spacing, of course, will reduce the bending moment, but the reduction is relatively minor. Okay? So here's an example. An 8-inch slab, and it's in warm weather, so we don't have to design for the negative thermal gradient. So plus 35 degrees C, that's very stringent. Okay? So the M crack, according to ACI 318, is 21.8 kilonewton meter per meter. So let's try one layer of 60 GPa GFRP, number 4 at 12 inches in the bottom in both directions. With GFRP, we can have a slightly smaller cover than steel, 2 inches. And so we found that the factor ultimate flexural capacity is 26. It's bigger than M crack. Okay? And then based on, although we have a 200 millimeter slab, we would use the response from a 6-inch slab, which is around 40% of the stiffness of the 8-inch slab. And we found that with the 12 kPa of uniform life load, the serviceability moment is 19.4, and that generates a tensile stress in the GFRP of 334 megapascal. which is around 0.3. So we're just good, okay? And then if we put a point load of 10 tons anywhere in that slab, it would generate a serviceability limit state moment somewhere between 21.2 to 27.9 over a certain width. So we use an average value of 24.5, okay? That would generate a tensile stress in the GFLP of 422 megapascal, okay? Now that is more than 0.3, okay? But we know some high-quality GFLP can actually sustain that. The bigger concern is fatigue, okay? If your slab is rarely used by a heavy truck like the 10 tons wheel load, okay, you may not have a fatigue problem, so you don't have this issue. But if you do, we have to make sure that the tensile stress is less than 0.4, okay? Here is a test that was done on a beam for fatigue, okay? And how do I, okay, all right. So this beam was tested, the maximum tensile stress is at around 40%, 400 megapascal, for over 2 million cycles. It didn't even fail, okay? So 40% is still a safe working stress for fatigue purpose, but we like to keep it like that, okay? Wrap up. Okay, this project in Australia, 7-inch slab, we reinforce it with 10M at 400, that means 10M at 16 inches spacing both ways. It was constructed in 2021, is working fine, upholding very well, no problem, okay? That's it. Thank you.